Hey, good morning. I'm happy that so many of you are here in this early time. So today I will talk about the right amount of abstraction for hardware. So what does it mean? Basically, I try to start very simple with a just simple Plinky thing, because in my opinion, even in a simple Plinky, it's not really clear what is a good way to abstract hardware in C++. In C you have many approaches to do that, and in C++ you have even much more possibilities. And in my opinion, it's not well researched what's the best option to do something like that. So I think from C you will all know something like this. That's the low-level C approach. I know, of course, even in C you can do some abstraction and maybe add some object-oriented approaches. But yeah, also sometimes you see something like that in your application code, and you don't want to do that because then your whole application code gets dependent on your hardware, and that's not what you want to have. So how do we want it to have? So this is really like, okay, can anybody tell me what it's doing out of the box? Okay, seems like not so easy. What? Yeah, it toggles an output register, yes. Okay, but I think it's not so easy to read it. If we have it in English, that's what it should do. If the button is pressed, the LED should switch on, else the LED should switch off. And that's how I want my source code to look like. So that's easy to understand, and I want my source code to be easy to understood. So in C++, you can write it like this. If the button is pressed, LED on, else LED off. And I think that would be very easy. So now the question is, how do I get there that I can write my code like this without having any overhead that is produced by the abstractions? And would you know how to do it out of the box? Which language features to use and which not? So one approach I see very often in C++ is we want to have as much as possible evaluated at compile time, and so most approaches I see there is they use templates, but in this talk we will see that there are also other possibilities to achieve that. So that will be our goal. Okay, and if we take it even further, then so I come from the modeling domain, so I work for a company that does a UML Code Generation. So our approach is to get even one step further, to not just code, but to model with like pictures. For example, some constructs like state charts are not very easy and readable to be programmed in code. So we think for this kind of stuff, it's good to have a code generator that helps you to visualize and generate code from that. So if we have time, I can show you something about this later. Okay, I think in this round it's not the question, should I use C++ for my embedded project? I heard many talks that were showing that it's possible, and that it's possible with no or low overhead. So the better question here to ask is, how should I use C++? So I don't want to convince you, so I want to discuss with you, what are the opportunities that I have. Okay, status quo C style. So many of our customers that work with modeling solutions are working with something like a ST chip, and most of them, the ARM controllers are getting so complex you don't want to configure them by hand. You don't want to go through the data sheet and write this whole initialization code stuff by hand. You want to generate it. So, and if you want to generate it, then yeah, the only possibility is to use a vendor-specific generation tool for that, because there is no abstraction that is not vendor-dependent, and there is no generator that does it. So the cmsys tries to do that, but it's not so very perfect, and it tries to emulate object orientation, but in my opinion it's not implemented so nice. But if we look here, what do we have here? This is the application code. So if you can't read it, we use the defines that we defined up here. That's generated by the code generator. Here I have my 2 pins. I configured them to be LED and button. And that's generated, this whole initialization thing, and this is how I use it in my application. The bad thing is, in every access to the hardware, I have to use this defines. So I have the hardware-dependent thing all over my place. So yes, I can abstract this too, but that's how it's generated. Another approach would be, for example, this is the cmsys Blinky that comes with, if you have microvision, I work with that most times. So there you have abstracted the LEDs just by number. That's not speaking very well too. And the button gives you a mask of all pressed buttons back. So you don't have the possibility for the API to just get one button. So you have to filter it or you have to wrap it again. So that's not what I want it to be. I want to be the driver, just like, yeah, simple to be used, object-oriented, and yeah. So some C++ samples. So embed is one solution that is out there, and there too is not thought to the end, but because some approaches are really nice. You have a digital out, and you can map it to LED1, for example. But for example, for the button, there is no preset defined. So you have to look at the pin again. And yeah, but the API, here you use operators to assign the LED to button. That's also quite nice. But there are some things that are not thought to the end. And that's another example, mod-m. I think some of you know that. What you see here, here, for example, we use static stuff. So the access is not with normal operation, with objects and operation calls, but it's with, here you have a namespace with a board, and you access the different peripherals via static thing. So that's an option that works with template, and that's an approach that is seen very often in embedded hardware C++ coding. Okay, what were my goals? My goals was to satisfy the separation of concern. That means I want to have the hardware code independent from my application code. I don't want to mix this. I want my application to be completely hardware independent. I know in deeply embedded systems that will not always work. Sometimes you have to implement some application code directly in hardware. So, or to use hardware features that are highly chip dependent. So there are exceptions, but in general, for easy stuff like GPIO or APIs that are good to abstract, I want to have my hardware dependency out of my application. Next thing is, keep the HAL as generic, but as simple as possible. I want to support as much controllers as possible, but it should be simple. It should not be blow you away. It should have low footprint and no runtime overhead. So I want abstraction, but I don't want to pay for it. And another thing is the HAL should be non-blocking. That means if we're not talking only about HAL, but also talking about runtime, then there are different approaches. There are some blocking or polling approaches, and there are also event-driven approaches. And I want my HAL to to be able to be used in every approach. So there must be a possibility to have non-blocking access, for example, for accessing, waiting for a UART input or something like that. So I want to work with callbacks or anything like that. Also, as I come from the modeling domain, I want my code or my hardware abstraction to be visualizable in a UML tool and to be easy to use there, and maybe just like the CubeMX configuration thing, that you have a picture of your chip in your model and just draw lines. Okay, this pin goes to this peripheral, this goes to this, and that's what I want it to be built up. So, and I want to generate the config for my special board. So I differ between controller and board. Controller is the single chip, and board is the thing when peripheral gets added to it. And then I will need to configure my controller to be connected to peripherals. And this pin configuration thing, I don't want to do by hand. I want to do this with tool aid, because then I can show up conflicts, that I don't use pins double, or that I know which pin can do what alternative function and something like that. So also here I want to have tool support. Okay, but another point is, how do I do that? I tried to start from the bottom up and abstract everything that is there. But that's an endless story. You can't do that. And it makes no sense for an abstraction, because if you want to stay generic, you can't abstract everything that is vendor dependent. So you can do the other approach and go top down. That's, for example, what you do when you write wrappers. Then you have your application, and you come from top down and say, okay, what do I need? And for this special thing, I write a wrapper, take a driver that's existing, wrap the thing that I need, and done. That's working, but in my opinion, that's not the best solution. Or you can mix both. So that's what I try to do. But I'm at the very beginning. I think other people like ModM is they're gone a far further way. My approach is to take the common stuff that might be useful for 90% of the applications, abstract this in a generic HAL, and provide implementations for that, but leave these implementations open for to be extended with stuff that might be chip vendor dependent, that you might use, but then you are aware of, okay, now I use vendor dependent stuff. That's okay if you need that, but in general, for most applications, maybe it will be enough to use the generic stuff. Okay, so I have many, many different code samples, and as you can read that way, we will step through the PDFs. Where are they? I have it not opened. emBO. Okay, so as you see here, I have many, many different options how to how to do it. Okay, let's start from the top. So I built that up that way, that I start with a simple way that is existing, and every main code looks like this, because it's getting more and more abstract and it adds layers. And the important thing is I benchmark this with different compilers and different optimization levels. We had a talk yesterday, and we learned that, for example, ARM6 compiler is much better for C++ than ARM5, and that's what I found out too. So we will see it here in the benchmarks. And yeah, you can, I compiled it, and then I passed the map file and got the code of the main. So everything, yeah, that's everything the main produces as code. So the first thing that we might know from C is we have a struct for our registers. That's a LPC 1768. And I just took out what I need to make it as simple as possible. And you know that's about registers. So the next level would be to try to abstract the registers in another way. So I don't know if you know it, but the header files, the device headers, are generated from SVD description files. And there is a generator for this, and you can generate them in different ways. You can use the normal approach, and you can use this bit field approach. Then the file generates you bit fields for that. That means you can access the bit fields here. It's a little bit better, but yeah, not what we want it to be. And so in the other slides, so maybe it's important to remember these numbers. So the 52 or something like the 50 is the optimal optimized code. And that's what we want to achieve. When something gets bigger than this, then we are on the wrong way, and then we have to readjust. So, yeah, in my slides, I would have the conclusions. So registers as struct, pro, these drivers are delivered by the vendor, but con is it's bad abstraction, and we have no separation of concern, it's not portable, and port and pin are needed for every access. That's important. If you look here, every time I access my driver, I have to type in these port and pin stuff, and I don't want to do that. So one next possibility is to wrap these classes in with functions, so that I, in my application code, don't have to write the special, the register bit shifting stuff, but I access this through functions. This adds a little bit benefit because it's easier to read now, but it is still lacking some features. It's still other direction. You have better information hiding. You can make less stupid stuff without having the bit shifting everywhere. But the API got easier, but still no separation of concern, still not portable, and still port and pin used everywhere. Okay, but as you see here, it's still optimizable. It gets a little bit bigger here, but it's still optimizable to the lowest. Okay, so here it's getting detailed, but here you can differ between passing a bit mask or passing a pin and do the bit shift inside the operation. That makes a difference in the code. So here with the 282 and with the bit shifting inside, you have 320. So if we compare the unoptimized thing, then this adds more overhead. But the question is, do we need to? In my opinion, let's focus on the optimized thing, and that's still good. Okay, so what we have here, yeah, if we go to the next level, then we will add a GPIO class or a digital IO class. So now we remember our port and our pin in an object-oriented approach. Now we think of a digital IO as an object and save our port and pin inside. So what we will have to do, only one time we have to initialize it with the port and pin. And every time we use it now, we can use it via the API and not have to use port and pin again. So Where are the slides? Here are the slides. Digital I/O class is now the first really object-oriented approach, and pin and port are only needed for one access, so that's wrong. The contrast, we still have no separation of concern and still not portable. If we look back here, we still have in our application, in our main, we still have our port and pin, so the main is not portable. Okay, what we can do about it? Now I will make a really quick step through the template stuff. You could also do it in a template way. And if you do it in a template way, you have again different approaches. So you can define a template. I think you all know this, with port and pin, and just use the template parameters here. And now this class can be used in different ways. You can use it as template classes with type defs. Then you have the point that you will need to access everywhere. You will have to use these static access operator. And if you have other peripherals, for example, that are abstracted in real classes and objects, then your code will be mixed all over. And in my opinion, that's not very nice. So I tried to just use the same driver, but just create objects out of it. So you might say, okay, why you do this? That's overhead. Let's stay small. But in my opinion, that adds the advantage that you don't mix access in your code. So in your code, everything is accessed by this point thing, or if you may pass it to another thing, you can have a pointer or something like that. Okay, and the point is, so we will have a look at the numbers later. Okay, maybe I open them so that's easier to be compared. Plots, code all. So now we are template static. And here, if you compare those three, template static, template object static, and template object static global, what does it mean? If you create objects, then you can decide where to create those objects, right? You can create those objects globally, so like here, or you can create your instances, your objects, inside the main. Do you know, will this make a difference? That will make a difference. So we will come to that so I need to do this like this. Oh. That's too much information. Okay, so static. Okay, so you notice here, if you use templates, it does not make a difference. If you use templates, then it will be all the same. The optimizer can optimize this all the way. So template static, or object static global have the same sizes. Okay, so let's go a little bit further. Object global, template object. Okay, now if you see this, what another disadvantage from this template stuff is, no constructor is called. So that means you cannot do any execution of code when it's generated. You just define a type and you can use it, but in the main application you have to, for example, call your configuration separately, so configure this as an input or output. So in my opinion, it could be nice to have it done on initialization. So what can we do? If we know that we are creating objects, we don't have to use static functions anymore. We remove the static, still remain the template stuff, and add a constructor, and in the constructor we can pass an additional argument, the direction, so we can decide it's an input or it's an output. Okay? So now we only have to call this, pass an additional argument, and now it's all done by this call. It's ready to use. So you see here, template, so I think that's 22. No, it's 23 already. So you have here, okay, so the step to this one is, here I remove the static. So from here to here, you see here is static and here is not static. You see, if I remove the static, then in unoptimized, it adds code, but the compiler can optimize it away. So it's okay. And so here still, if we use this global as global instances, still can optimize it away. And here we have some, this is what I have shown you right before with the direction, with this additional argument. And then another possibility to approach this input-output decisions thing would be to add additional classes and not use digital I/O, but use digital input and digital output that inherit from digital I/O, and they have the constructor and they do the initialization. That has another advantage. You can see here in the name it's an input or it's an output. So it's just, yeah, if you like this more, to have it here readable, or if you have it here readable. The disadvantage of this solution is you have an additional layer of classes you have to inherit, and you have to have another layer. And if we go to the code, what's this? Okay, these are the three. Just digital I/O with a third parameter direction, or not digital I/O but digital in and digital out. And if you see here, all three, this grows a little bit in size if you add the third parameter with the constructor in unoptimized but not in optimized. In optimized, it's all fine again. Okay, oh, what's going on here? What's going on here? Now we add interfaces. So maybe we will make our application really independent. So we want to have our application use the digital I/Os via interfaces. So now we define an interface, digital I/O, that has virtual functions for high, low, and for these. And we tell this class to implement this interface. So this would be the normal C++ approach with dynamic polymorphism. Okay, what happens now? A really interesting thing. If we now place those objects with this interface usage in global space, will he still be able to optimize it away? No. And that's an important thing, because that means if you are using something like that and you want to be able to optimize the way, you have to place it inside the main, because then he knows, the optimizer knows better about it. And here you see also an interesting thing. The blue is the ARM5 compiler and the red is the ARM6 compiler. And here you see for this, when you place it in the main, the unoptimized of ARM6 is much bigger, but it can be optimized away completely. And in ARM5, the unoptimized is not so big, but it also can be optimized away. And later we will have examples where ARM6 will be able to optimize it and ARM5 won't be. So in the first iteration of this Stadt stuff, I only used the ARM5 compiler, and I thought, okay, I can't use it because the compiler can't optimize it away. But with this, I found out, okay, it's not about the language feature that doesn't work, it's about the compiler that's not able to optimize it. Okay, so what's the time about? We could go through all of the other examples. We add more abstraction. For example, here now we start to leave the templates out and just have our digital I/O and use the constructor to pass the port and pin, and just store it in const variables. And you will see if we use digital I/O, it's still optimized away. It's a little bit bigger, but it's still optimized away. And here too, here is the, okay, so this is the digital I/O. That is, in my opinion, the final version. So we store, here we store the pointer to our register and our bit mask, but we pass a port number and a pin. So in the API, it's very simple, just an enum, port, and pin. And the mathematical stuff, the bit shifting, and it's done one time when assigning the variables, and then it just acts as bit mask and address for the register. And we have different possibilities to initialize. We have the possibility to initialize just by port and pin and make it like this, digital output and input. We have the possibility to add a third parameter because we have different constructors that are overloaded. Or even better, we have the possibility to do this. What does this mean? Now, we only pass an initialization struct to the constructor. And what benefits does this add? So it's a little bit stolen from the ST library approach. They also use init structs, but in a way that is, in my opinion, not so useful. If you use it in this way, you can make your application completely independent from your hardware, because in your application you only use the init structs. And you have to know, of course, which init structs you have. You have to define this like an interface. So for example, I have an LED and I have a button, that's all. And then my contract is deliver me those init structs, and I will use it and initialize my thing. And so you can put this into a separate header. This header can be generated from a pin config tool. And in my application, I will only use those init structs. Okay, but what you still have, if your application grows, you will have to, to improve the architecture, you have to add more separate things. So not one application should contain all hardware. You want to be a little bit more flexible, and we don't have to go this in detail. But one thing would be to, one other level you could add is to, many code. For example, do something like this. In the examples before, you had here digital I/O read and write. And that's nice for a digital I/O, but in normal cases in your application, you don't talk about GPIOs, you talk about peripherals. You talk about turning a motor on or off, or turning a motor slow or fast, or turning an LED on or off, or ask if a button is pressed or not. So I want to make my application more speaking. So I want to add another abstraction and say, okay, we have buttons and LEDs now, or we could have motors or sensors or stuff like that, but it's another abstraction layer. So in my application, I don't see anything about GPIOs. I only see the peripherals, the next level. So, and if I see here, I add another level of abstraction, even with interfaces and stuff like that, and the compiler can still optimize it away. It's still gone. Still just the lowest 84. Okay, now we can encapsulate this in a board class. So that was my first approach to get the hardware-dependent pin and port stuff out of the application. But with the init struct, that gets kind of not necessary, because your init struct also does this to get your board-dependent pin and port numbers out of your application. Okay, so do it. What is a little bit more sensible to me is to have something like this, to have to pull your application out. So maybe you have let's look at let's look at this. That's, for example, you have an application and you want your application to use this button and this LED. And now you only say you only know the interfaces, you don't know the implementation. So that's a little bit in object orientation, you have the classes and the instances. And so the question is every time, where do I instantiate stuff and how do I connect stuff? And for example, in this approach, I could say the application not has a button and a LED, but just knows them via the interfaces. That really makes it abstract, because I can have different applications on my system and specify which application knows which hardware. So I don't have to have this global stuff, so I can connect in detail. This application will be connected to this LED and to this button. And this, for example, is one thing that you could then use in the generation tool. And so it would look like this. So maybe let's struct. So yeah, I would do it like this. I would say, okay, so that's the most abstract way. I will have the digital IOs generated somewhere with the init structs, so they are generated independent. Then I will have my peripherals. I connect my peripherals to my pins. That can be done in a tool by drawing lines. And then so this will be the thing that can be generated by a tool by drawing lines. So the button has a digital in to be used, and you have to connect it. Here it's done by a setter, and you could generate it. And the application also uses a button and LED, and this could also be generated. And you would say, oh, what an overhead for a simple Blinky thing, but your application will get more complex, and maybe you will be happy to have this abstraction. And what do we see? Unoptimized. It's really blowing away, but it's still optimizable to the smallest code. And here, you will notice, when you have this amount of virtual stuff and things going on, then ARM6 will be able to optimize it away, and ARM5 not. So, okay, this was the last. Okay, now go back to the slides. I think maybe you are confused about this whole code stuff, but for me it was important to get a feeling for what possibilities are there and what is optimizable and what not. And maybe we will not have time for discussion because I want to show you some other stuff, but I would be happy to, we have this discussion round in the evening. So maybe if you are interested to discuss about this stuff, let's talk in the evening. So, okay. What have all the solutions in common? So this application, what I showed you, was blocking the processor all the time because in the while else loop he asks every time, is a button press? Yes, okay, LED on. Is a button press? Yes, LED on. And in normal applications, this might not be the thing you want to do. You want to, so the information flow in this application is you have a button and the button needs to recognize a change. And then when this change happens, then the LED should do something. And the other time, it would have to do nothing. So the next step in abstraction would be to fix this information flow so that and add in something like event-driven paradigm to only do things when it's necessary. And that, of course, needs to change in architecture. I need to add some, so I have different possibilities. I can use interrupts for that directly, or if I don't, then I have to poll in a certain speed to convert the signal stuff into an event-driven stuff. And yeah, for me, it's also an important point in this abstraction. But if you use this, then it will be much more easier to have a modeling tool to support this. This was some ideas from me to how to build up such a framework. Maybe I'll just step over it because it's not very readable. So in my opinion, this line is the hardware independency line. So everything down here is hardware dependent because you have hardware, you are on embedded, and everything up here is completely hardware independent. I don't know anything about the hardware, and that's the thing with those init structs, for example. You find it here. This is the pin config tool, and with the pin config, no, we start here. This lower level, that's the HAL driver code. That's the digital I/O class. You have it here in a model representation. In my domain where I'm working, that's UML, but you can think about other stuff. ModM, for example, doesn't use UML. It uses other model stuff to abstract this. And you have a code generator, and from this code generator you generate the driver code. So that's my digital I/O class. That's one way you instantiate those classes that you generated. For this, you need another generator. You need a pin config tool generator that generates your init struct out of your chip configuration. And then you have here a package with HAL objects, or so in my actual opinion, that will not be the HAL objects itself, because when you have the objects generated somewhere, then they are global, and what we saw, global is not good to be optimized away. So actually, I think this should be the init structs that are generated by the pin config tool, and your application should instantiate that's the thing that I call board interface specification. That's what my application expects from the board. For example, my application expects the board to have a digital I/O for the button. And here I instantiate and use it in my application, and it will be completely hardware independent. So that's an idea. Maybe we can discuss about it in the evening. Okay, so 9 minutes left. Okay. So, okay. When we talk about scheduling, event-driven does not mean async. So, there are many different ways of realizing those callback and event things. You can do it synchronous by just having callback operations and execute the stuff directly when it happens. That's fine as long as it goes fast. But as soon as you have things that take a little bit longer, then you will want some asynchronous mechanisms added to it. But that's, that's another level. In my opinion, you have to like separate it. So there's always a question: do you want to pull your dependency to asynchronous stuff in your interfaces or not? So we will look to UML Code Generation, and then you will maybe see what I mean. And the point is, most architectures most applications will have to mix different scheduling approaches. So in most applications, or in some applications, I might have controller loops that needs to be on time, really hard. And I have asynchronous stuff that happens sometimes. And I will also have to, schedule this. And so that's what, that's a slide of my boss in my company, Andreas Willert. He talks a lot about this stuff. In modern systems, you will have to mix scheduling panels. So you have so it's German, you have some time-triggered scheduling for the controller, for example, and you have some event-driven scheduling. And the thing is, in your electronic stuff, it's all like time-driven or signals. It's continuous. So in some point, you have to convert it into events, or you have to pull it and make it discrete for time-triggered scheduling. And then you have to pull it back together and make signals again out of it. And it might be really hard to maintain an overview over this whole stuff, what's going on in my scheduling, and yeah. So, what can I do, or how can I know that things are working properly? And in my opinion, one good way is to use abstraction and to have everything in a common repository. For example, if you have different, we will look at the stopwatch, if we have different elements that are using the polling thing, the polling paradigm, then I want to see all of them in one view to maybe be able to recognize conflicts. And you can do it in the time of creating the application by making assumptions, how long will it take, and then you, in the next level, you can execute it and get your data back and verify if your assumptions were correct, and then readjust and do it like this. So this is, in my opinion, one approach that can lead to success, that you can have tool support to get your information together and to filter out the information that are relevant for you. So I only have 5 minutes. Let's do it. Let's look how this looks in the real thing. Oh, I lost my microphone. Okay, so how does it look like in UML? We use Rhapsody as a tool. Here, that's how our hardware abstraction looks like in UML. Is it big enough or? No. Oops. So I have the two interfaces, digital input, iDigital input and iDigital output. That means I can separate which one I want to use. they go together in a combined interface, and then we have the concrete realization. And this realization is also kind of poor man's interface, sometimes I call it, because if you see this, there is nothing chip dependent in this. So if you create an object and use only the init struct, then it will be also a kind of like interface even in the implementation. So what is the application about? 3 minutes left. Let's go fast. Okay. Good timing. So my application will be a stopwatch that can be resetted, stopped, or running. And one big advantage is if I have it in a model, I can simulate it. So now I'm running it in my system here. And I can use a panel diagram to trigger it. And I can start it, and the output of the stopwatch is just the printf thing. It's a little bit small. But you see here in the printf thing, the stopwatch is running just like here. So you can start it, you can stop it. You can also animate state charts, you can do simulation. You can do your application level just without any hardware. Okay? Now I use the same application, just switch the scope and bring it to the target. Now my architecture looks a little bit like this. So I will not go into detail, but this is the hull driver stuff. These are the hull interfaces. Then I have some peripheral drivers built on top of the hull that uses it and adds some state behavior. So if I want to make my button a click and hold button, I have to do some polling and timing and do a decision when is the hold time over, and then I will send a callback. This callback then goes to a click and hold button handler, and this handler can do stuff, and this handler here is implemented special for the application. That's why this package is something like connecting the peripheral drivers and the application. The peripheral drivers only have the callback. Here I have the implementation, and this implementation then sends an event to the stopwatch. Okay? How does it look like when we run it on a target? Okay, it's still running, so we have to quit it. So, run it on the target. So, now you have to build it, flash it, and so on. And our approach is not to do it in the UML tool, but to deploy to an ID project. For example, Microvision here. I connect my board. Connect with Windows. 33 seconds left. Okay, and now debug. And now the same model, the same application model runs on my target. I see here, you see, I just used the printf debug output to keep it simple. I also could use the display. You see the stopwatch here. I press the button, and the stopwatch will start running. And it's the same application in simulation, and on the target, I only cut off the hardware layer or the things that are below, and it's running. Yeah, thank you. That's it.